Welcome to this explainer. Are you stressing over the Cambridge 9618 binary trees syllabus? Hey, take a deep breath. I'm going to be your tutor today, and we're going to treat this whole concept like a simple family tree sandbox. It's really not as scary as it looks. Let's conquer OOP, insertion, and traversal together, step by step. So first things first, what actually is a binary tree? Well, just think of it as a super strict family tree. The golden rule here: every single parent node is allowed a maximum of 2 child nodes. No more, no exceptions. That's literally it. Let's meet the family. Up at the very top, you've got the root node. That's our ultimate ancestor. The lines pointing downwards, those are your branches. And right down at the very bottom, the nodes that don't have any children of their own, those are called the leaves. Now, to actually build this structure inside a computer, we use object-oriented programming. If you're a little fuzzy on this, think of a class as just a paper blueprint for a family member. An object, on the other hand, is the actual living, breathing family member that we create from that blueprint. Let's take a look at our Java blueprints here. Notice how the node class holds our actual data, plus those crucial left and right pointers. The binary tree class, it's incredibly simple. All it does is hold that starting root node. Once that's set, the nodes basically just link themselves together from there. Adding a brand new node is basically just 4 super simple steps. You compare the new item to your current node. Is it smaller? You step left. Is it larger? You step right. And you just keep stepping down the branches until you find an empty spot. Boom. It literally sorts itself as you build it. Let's look at the actual code for this. When you see if item is less than node.item, insert left, that's just the computer asking a simple question. Hey, is this new number smaller? If the answer is yes, it takes the left path. And it keeps asking that exact same question until it finds an empty home. Imagine following a blue path down the left side of our tree. 16 is smaller than 27, so it goes left. Then it's smaller than 19, so it goes left again. That blue route you're picturing is exactly what our less than code looks like in action. But what if the number is bigger? That's where our else if statement comes in. Else if item is greater than node.item, insert right. The computer just pivots its attention and steps down the right branch instead. Let's trace an orange root for these larger numbers. Say we have 42. It's bigger than our 27 root, so we step right. It's bigger than 36, so we step right again, and boom, we found its perfect sorted spot. All right, so this family tree analogy is great for picturing it, but what does this actually look like under the hood in the computer's memory? Because as we know, computers don't have literal tree branches growing inside them. To really nail this Cambridge exam, we have to know how the memory maps this out. Underneath it all, the computer is actually just using a standard 1D array to manage all these pointers. Our root, 27, is sitting right there at index 0. Its left pointer tells us to go to index 1, and its right pointer says go to index 2. And hey, see those negative ones? That's what we call a null pointer. It just means we've hit the end of the branch. No more children. Now here is absolutely the best news for you. Inserting a node and searching for a node, they use the exact same logic. That whole left for smaller, right for larger rule works perfectly for both building the tree and searching through it. You only have to learn it once. Take a look at this search algorithm. See that while loop? It just keeps running, checking our golden rule. Smaller go left, larger go right. It's basically just following a trail of breadcrumbs until it either finds the exact number you're looking for or it hits one of those null pointers. Let's do a trace table walkthrough and search for 42. We started our root, which is index 0, holding item 27. 42 is bigger, right? So we check the right pointer, which sends us to index 2. At index 2, we find 36. 42 is bigger again, so we check its right pointer, which tells us to jump to index 3. And there it is, we found 42! Okay, your turn. Let's do some Cambridge practice. If we want to search for the number 55 in this tree array, what exact path of index numbers do you need to take? Take a second and remember our rule. Larger goes right, smaller goes left. All right, let's trace it out together. We start at the root, index 0. 55 is larger, so we go right to index 2. It's larger than 36, so we go right again to index 3. Larger than 42, so we go right to index 5. But wait, 55 is smaller than 89, so we pivot and go left to index 8. And there it is. Found it. See, you've got this. Just look at what you've mastered today. You've built OOP blueprints, you've planted a root, and you've navigated through complex memory arrays. These intimidating computer science topics are really just simple building blocks working together to make an elegant, self-sorting structure. Before we wrap up this explainer, I want to leave you with one final thought. If a binary tree automatically sorts its data by branching left and right as it builds, what on earth happens to its overall shape if you insert a list of numbers that are already perfectly ordered, like 1, 2, 3, 4? Think about that for your next study session. Keep practicing, and I'll catch you next time.